Welcome back. The topic of this interactive video lesson is on real functions problems. Let's start with an overview. In this lesson, we'll practice what we have learned about functions and their graphs and solve some story problems. The problems will involve 5 types of functions and graphs: periodic functions, piecewise functions, step functions, quadratic functions, and exponential functions. Let's review some of the key points about each type of function. Let's start with periodic functions. A periodic function repeats its values in regular intervals or periods. A periodic function can be built by taking the initial period or cycle and continually translating it horizontally. This cycle has a period or length of 6 units, or p equals 6. The y value at a given x value equals the y value at x plus p. We see that f of 2 equals f of 8 because x equals 2 and x equals 8 are 1 period apart and they have the same y values. Now let's look at piecewise functions. Piecewise functions consist of 2 or more pieces. For example, this would be a piecewise function. We match each equation with its section. First, f of x equals x when x is between 0 and 10. F of x is 2x minus 10 when x values are between 10 and 15. F of x is negative x plus 35 when the x values are between 15 and 20. When the x values are between 20 and 25, we use equation 4. And when the x values are between 25 and 35, we use equation 5. Use the domain to help you find the x-axis. Use the x-axis to identify points on the y-axis. For example, use equation 2 to find y when x equals 10. Substituting, we simplify, and we see that y is 10. Now use equation 3 to find y when x is 15. Substituting and simplifying, we see that y is 20. Use equation 4 to find y when x is 20. Substituting and simplifying, we see y is 15. And use equation 5 to find y when x is 25. Substituting and simplifying, we see y is 5. For what values of x is y greater than or equal to 10? Well, that would be these values here. We can see that y equals 10 when x equals 10 from the graph. What is x when y equals 10 in equation 4? Well, substituting, 10 for y, and solving, we'll subtract 55 from both sides, and then divide both sides by negative 2, and we see that x is 22 and 5/10. So y is greater than or equal to 10 if 10 is less than or equal to x, which is less than or equal to 22 and 5/10. Now let's look at step functions. Similar to piecewise functions, step functions consist of pieces that resemble horizontal steps. For example, here's a step function. A small town has a bike rental service that charges $4 for anything less than 2 hours, plus $2 for every additional 2 hours, or any part of 2 hours. You would pay $4 to rent a bike for 1 hour and 30 minutes. You would pay $10 to rent a bike for 6 hours and 0 minutes. Ignore the open dot and look at the closed dot in this case. If you were charged $14, your time of use was somewhere between 10 hours and 12 hours. Notice we can include 10 hours, but not the 12 hours. Now let's look at exponential functions. The exponential function with base c is defined by f of x equals c to the x. Remember that exponential functions are often used to model situations involving growth and decay. When the c value is between 0 and 1, the graph is decreasing, and it can be used to model decay. It would look like this. When c is greater than 1, the graph is increasing, and it can be used to model growth, and it looks like the graph in red. But what happens when x equals 0 and y equals 1? Well, that's this point right here. The exponential function often has a parameter a added like this. Notice it's the 2 in front of both of these. It would modify the graph like so. We say that parameter a represents the initial state of the equation because in real-life applications, the x-axis often represents time. When the growth or decay process begins, no time has passed yet. In other words, x equals 0 and y equals a. In growth and decay situations, c represents a factor of change. If an initial population of 100 cells doubles every hour, a equals 100, c equals 2, and x equals the number of hours. This situation can be modeled with this function. Notice, since the c value is greater than 1, this is growth. If an initial population of 10,000 people is halving every year, then a equals 10,000 and c equals 5/10, and x of course equals the number of years. Here's the function to model this. Since the c value is between 0 and 1, this represents decay. If the initial value of a home is $300,000 and it increases in value by 6% every year, well then a would be 300,000, c would be 1 plus 0.06, which is 6% as a decimal, and x is the number of years. Here would be the function to model that. Notice, since the c value is greater than 1, we have growth. Let's look at another. If the initial value of a car is $25,000 and it decreases in value by 10% every year, well then a is 25,000, c is 1 minus 1/10, which is 9/10, and x is the number of years. So when we increase, it's plus, and when we decrease, it's minus. Here will be the function for this last one. Notice since the c value is less than 1, it's decay. If we're solving for f of x or y, we substitute the values for a, c, and x into the equation and calculate. If an initial population of 100 cells doubles every 2 hours, how many cells are there in 10 hours? Well, 10 hours per 2 hours per unit means that x equals 5. Here's the function for this. Substituting 5 for x, we can simplify. Remember, we follow the orders of operation, which says we do exponents first, then we multiply, and we see that f of x is 3,200 cells. Now, if Sean buys a car for $25,000 and it decreases in value by 10% every year, what is its value after 3 years? Well, decreases by 10% means that each year the value is 90% or 9/10 of the previous year's value. This is also 1 minus 10% or 1 minus 1/10. This is the function that it would look like. Substituting 3 for x, we simplify. Following orders of operations, we see that f of x is 18,225. So that's what the car would be worth after 3 years. If we're solving for x, the length of time that has elapsed, we need to create a table of values and calculate y for various time increments of x. When we arrive at the sought value for y, we know we have the sought value for x. For instance, the population of Middleton was 10,000 in January of 1995. If the population decreased 4% every year, in what year was the population 8,847? Well, a 4% decrease means to multiply by 96 hundredths. So the rule for calculating the new population y is 10,000 times 96 hundredths raised to the x. Now make a table of values showing the population after 1, 2, 3, etc. years. So year 0 is the year 1995, year 1 is 1996, and the population is 9,600. Year 2, 1997, the population is 9,216. In 1998, that's year 3, which is around 8,847. So the population dropped to 8,847 by January of 1998. Now let's look at quadratic functions. The basic quadratic function is defined by f of x equals a times x squared. We can use a quadratic function to solve problems involving rectangles like this. The length of a rectangle is twice as long as its width. What is the length and width if the area is 72 square centimeters? Well, let's draw a diagram. If we labeled one side x, the other side would be twice as long, or 2x. We know the area is length times width, so we substitute. Multiplying those together, we know the area is 72, so we'll substitute, divide both sides by 2, and then take the square root, and we see that x is 6. So the width is 6 centimeters. That means the length is 12 centimeters. Let's look at another. A plan for the half-pipe in a skateboard park uses a quadratic equation to describe the shape. If they make the half-pipe 8 meters tall, how wide will it have to be? So substituting 8 for y, we can divide both sides, and then take the square root, and we see that x is 8 meters. All right, now you're ready for more examples in practice.